Hi everyone. So in this video, we're going to continue to talk about trigonometric functions. Specifically, we're going to learn about 3 additional trigonometric functions, but don't worry, they're basically just defined in terms of the 3 we already learned, so it's not a lot more to learn. And then we're just going to do some more practice problems and some problems that kind of approach trigonometric functions a little bit differently. So I want to start with just doing a warm-up problem because what we covered in the last video is just so important. We want to make sure that, I want to make sure that you retained what we learned in the last video. So pause the video and try this yourself. So you want to evaluate sine, cosine, and tangent of the angle negative 13 pi over 6. Okay, so how would we tackle this question? Well, remember that evaluating sine, cosine, and tangent of an angle basically comes down to finding the terminal point of that angle. And so the first thing we need to do is we need to figure out, what does this angle even look like? Where is this angle on the unit circle? And then that will help us to determine its terminal point. Okay, so our angle is negative 13 pi over 6. So we can already tell that angle is not going to be between 0 and 2 pi because it's negative. But it's negative, but it's more negative than negative 2 pi, right? Negative 2 pi would be negative 12 pi over 6. So negative 13 pi over 6 is definitely more negative. And so that means that probably the best way to kind of tackle this angle is to figure out, it's going to be negative 2 pi minus some additional angle. And if we can figure out what that additional angle is, well then, negative 2 pi will just mean going around in the circle once. So that's not really going to affect the terminal point. Really, the important part is figuring out what is that extra piece. So how would you get from negative 2 pi to negative 13 pi over 6? Well, negative 2 pi, as we mentioned, that would be negative 12 pi over 6. And so what do we need to subtract from that in order to get negative 13 pi over 6? Well, just an additional pi over 6. So that means that negative 13 pi over 6 can be written as negative 2 pi minus pi over 6. And so that tells us that this angle is going to involve, so 2 pi, regardless of whether it's positive or negative, is always going around the circle once, one full rotation. Negative 2 pi means that we're going in the clockwise direction. So negative 2 pi, that part would look like this. But then we want to go further by another pi over 6 and continuing still in that negative direction. So basically that's going to put us like right here. So we're going to have an angle that looks similar to actually negative pi over 6. It's just negative pi over 6 with that additional rotation. Let me just clean this picture up a little bit. So it's basically like this. Okay, so that's our angle. That is negative 13 pi over 6. All right, so now we need to figure out what the terminal point of this angle is. And so that's where this idea of these special right triangles come in, right? And so if we were to draw a triangle like this, it would be a 30, 60, 90 triangle. And so I'm going to draw it down here a little bit bigger. And by the way, like once you've done this for a little bit, you don't need to always redraw the triangle. You'll probably kind of get a sense of, okay, I can tell that's a 30, 60, 90 triangle. I can tell which side is which. You don't always need to actually draw the triangle like this, but I'm going to do it for now. So this angle at the top, this is going to be pi over 6, right? Because the angle we're working with was basically like 2 pi plus an additional pi over 6 just going in the negative direction. And so that means that this angle is pi over 3. And so the sides of our triangle are going to be, the hypotenuse we mentioned is always 1. The longer side is square root of 3 over 2, and the shorter side is 1/2. And then all we need to add into that is basically the sines, s not sine like the trig function, sine sign of those two coordinates. So because we're in quadrant 4, we can tell that the x coordinate is going to be positive. So the x coordinate is coming from this side, right? Square root of 3 over 2. So it's going to be positive square root of 3 over 2. and then the y coordinate is going to be negative. And so that's going to come from the 1/2, but we have to make it negative 1/2 because it's in the negative direction. Okay, so now we're ready to evaluate sine, cosine, and tangent. So to evaluate sine, that's always looking at the y coordinate of the terminal point. So the y coordinate of the terminal point in this case is negative 1/2. And then cosine, that is looking at the x coordinate of the terminal point. And so that is going to be square root of 3 over 2. And then to evaluate tangent, we need to divide sine by cosine. So basically the y coordinate divided by the x coordinate. And so that's going to be negative 1/2 divided by square root of 3 over 2. And so in the last video, I showed you how, if you're dividing by a fraction, you can rewrite it as multiplying by the reciprocal of that fraction. So you're welcome to write it like that. The other thing that you can notice is basically because of that rule, what's going to happen is that if you have the same denominator in both of these, they're going to end up canceling out. So if you don't quite follow why that works, then totally just rewrite it as multiplying by the reciprocal. That will guaranteed get you to the right answer, but it just works out that if they originally have the same denominator, when you flip the bottom one over, it's going to cancel out with the other denominator. And so this is going to simplify to negative 1 over the square root of 3. And as we saw in our last video, we can rationalize the denominator, so we can multiply by square root of 3 over square root of 3, and that's going to give us negative square root of 3 over 3. And one thing I mentioned in the last video was that at the very end of the last video, we talked about how tangent is the same as the slope of that terminal side. So if you looked at like this, I'm highlighting it right now in the lighter green. If you look at the terminal side that we drew, if you found the slope of that, that should be tangent. Now that's not super helpful in actually evaluating tangent. To find the exact value of tangent, we do need to actually divide sine and cosine. But it is helpful just to do a quick check just about whether it should be positive or negative. So looking at the slope of this terminal side, it's negative, right? It has a negative slope. It's going down from left to right. And that agrees with the fact that we found that tangent was negative. So that's just kind of one quick check you can do to make sure that you didn't make some kind of mistake with your signs earlier on. Okay, so that's sine, cosine, and tangent. So as I mentioned at the beginning of the video, we're going to learn 3 more trig functions, and each of these I'm going to call the reciprocal trig functions. And the reason they're called the reciprocal trig functions is because they are the reciprocals of the original 3. So the first one we're going to talk about is the reciprocal of sine. So the reciprocal of sine is called cosecant. So cosecant is the reciprocal of sine. And I'll write down the abbreviations for them in a moment. I just want to first introduce the full names of each of them. So the reciprocal of cosine, well, that is called secant. And then the reciprocal of tangent is called cotangent. So I would say that students usually find this one pretty easy to remember, right? Cotangent, tangent, they kind of just sound like they go together. I know that these two almost feel backwards. It's like, why is this one co and that's going with sine, and then this one doesn't have the co and it's going with cosine? And that's actually how I remember them. I just remember that it's kind of backwards of what I would expect. So, we have cosine and we have sine, and they basically go with the ones that are kind of opposite of them. So, sine starts with an S, cosecant starts with a C, cosine starts with a C, secant starts with an S. So they go with the ones that are kind of flipped from the original function. Okay, so I want to write out now the abbreviations for these. So cosecant is abbreviated as CSC. So we would write CSC of theta. And then what do I mean when I say it's the reciprocal of sine? That means that it can be written as 1 over sine of theta. So basically, we'll see this in a moment, but the way we're going to actually calculate the reciprocal trig functions is just to do the original trig functions and then take the reciprocal, do 1 divided by each of them. So secant, the abbreviation for that is SEC. So secant of theta, and actually I've been using parentheses. Like I mentioned this in the last video, you don't have to put parentheses. I kind of like to do them because they emphasize that the angle is kind of like an input. So secant of theta can be written as 1 over cosine of theta, right? Because it's the reciprocal of cosine. And then finally, we have cotangent. So cotangent of theta, the abbreviation is COT, and that can be written as 1 over tangent of theta. Okay, so first example, let's evaluate cosecant, secant, and cotangent of negative 13 pi over 6. So as you may notice, this is the same as the first example we did in this video, the same angle, right? And so what we're going to do is just use the information that we already found in our warm-up problem to answer this. So let's start with cosecant. So we know that cosecant of negative 13 pi over 6, the way that we're going to calculate that is we're just going to find the reciprocal of 1 over sine of negative 13 pi over 6. Because that's the definition. That is what cosecant is. And so if we go back and remind ourselves, what did we find in this question? We found that sine of negative 13 pi over 6 was negative 1/2. And so we want to take the reciprocal of negative 1/2. So we can rewrite that as 1 over negative 1/2. But remember, doing 1 divided by something is it's the same as flipping that number over. And so you don't even really have to write this step down. If you know that sine is negative 1/2, you can just take the reciprocal. So the reciprocal of negative 1/2 is negative 2. So it's just taking whatever fraction you had for your original trig function and flipping it over, basically. Or you can write it like this. It doesn't really matter to me which way you do it. Okay, so similarly, if we want to find secant of negative 13 pi over 6, that's going to be the reciprocal of cosine of negative 13 pi over 6. And so if we go back and remind ourselves what cosine was square root of 3 over 2. So we're going to take the reciprocal of square root of 3 over 2. So that's 1 over square root of 3 over 2, which is the same thing as 2 over the square root of 3. So literally just flipping over the result that we got for cosine. And then as we've been doing, we can rationalize this denominator by multiplying by square root of 3 over square root of 3. As I've said, that really is optional. I don't mind if you just leave it unrationalized, but it's a little bit more typical to rationalize the denominator, and that's why I do it. Okay, finally we have cotangent. So cotangent of negative 13 pi over 6, that's going to be the reciprocal of tangent. So we're going to do 1 over tangent of negative 13 pi over 6. And so if we remind ourselves what we found for tangent, we found that tangent was negative root 3 over 3. But actually, I think it'll be more useful to go back to this version, because notice that if we, so these are the same, right? These two numbers are the same. It's just two different ways of writing the same number. But remember, we're going to be taking the reciprocal of this number. So if we take the reciprocal of negative 1 over square root of 3, then the square root will be in the numerator. Whereas if we take the reciprocal of this other one, the one in the box, the square root will be in the denominator, and we'll have to rationalize the denominator again. So we can kind of skip that rationalization step if we just start with the one that's written in the circle here. So it's going to be 1 over negative 1 over square root of 3. So 1 over negative 1 over the square root of 3. And totally fine if you want to use the other one. It will just take you an extra step if you want to rationalize the denominator. So what is the reciprocal of negative 1 over the square root of 3? Well, that's just going to be negative square root of 3, right? Flip it over and it would be negative square root of 3 over 1, which is just negative square root of 3. So that's it. That's how this works. It's really, if you know how to find sine, cosine, and tangent, it's really nothing too new. It's just taking the reciprocals of those things. Okay, so we're going to do a couple more practice problems, and we'll see that these bring up a couple of new things that can happen with the reciprocal trig functions. So first one I want to do is evaluating all trig functions for the angle theta is equal to 5 pi. So let's start by figuring out what the angle 5 pi looks like. So 5 pi, we can definitely tell that that is bigger than 2 pi, right? And so how much bigger than 2 pi is it? Well, it's actually even bigger than 4 pi. So remember, any integer multiple of 2 pi equals a rotation around the circle. So if we look at this as being 4 pi plus pi, well, this 4 pi part, that doesn't really affect the terminal point, right? The 4 pi part is just going to be going around once, so that would be 2 pi. Around again, that would be 4 pi. And then the extra pi will take us to 180 degrees. So in this case, it's enough bigger than 2 pi that we don't want to think of it as 2 pi plus something. If you did that, you could, but you would still have like another 2 pi that you could pull out from it. So we might as well first write it as 4 pi plus pi. So basically the idea is that you're pulling out any even multiple of 2 pi is just going to be going around in the circle a number of times. And so this is the important part. This is the part that actually tells us where the terminal side and the terminal point are going to be. So this is 5 pi. And so our angle looks like this. And so this is one of the ones where we don't have to draw a triangle to find the terminal point, right? We can just kind of look at the picture and use that to figure it out. So this is going to be -1, 0. Okay, so let's evaluate all of our trig functions here. So we're going to do sine, and then maybe after that we'll do cosecant, which is the reciprocal, and then kind of go through them in pairs. Okay, so what is sine of 5 pi? Well, sine of 5 pi is going to be the y-coordinate of the terminal point. So what is the y-coordinate of the terminal point? In this case, it's 0. And so that's it. Sine of 5 pi is just 0. So what do we get if we try to do cosecant of 5 pi? Well, remember that cosecant is supposed to be 1 over sine. It's the reciprocal of sine. And so in this case, that would give us 1 over 0. And so that is undefined. So this is something we saw happen with tangent. We saw that sometimes tangent can be undefined, and we'll see that the same thing can happen with the reciprocal trig function. So if sine is 0, then cosecant is going to be dividing by 0, which will be undefined. So what is cosine of 5 pi? Well, now we're looking for the x-coordinate of that terminal point. And actually, I forgot. Let me just do my little color coding here. I like to do that. So this is -1 was the x-coordinate, and 0 was the y-coordinate. Okay, so what is cosine? So that is going to be the x-coordinate of the terminal point, which is -1. And then secant of 5 pi, well, that's going to be the reciprocal of cosine. So in this case, that's going to be 1 over -1, and that is -1. So that one is fine. It's not undefined. Okay, finally, we have tangent and cotangent. So tangent of 5 pi. So remember that tangent is the y-coordinate over the x-coordinate. Or this is one of the cases where you can think of it as slope, because you can tell that this is a horizontal line. So the slope is 0. But let's just do it as the sine over cosine. That would be 0 over -1, and that would give you 0. And so now we can see that cotangent is also going to be undefined, right? Because cotangent is supposed to be the reciprocal of tangent. And so 1 over 0 is undefined. So basically, I'm showing you this example to demonstrate that for the reciprocal trig functions, they can be undefined. All three of them can be undefined at certain parts of the unit circle. And so we'll see another example kind of like that here as well. Okay, so maybe if you didn't on the last one, on this one, pause and try it yourself because it's going to be fairly similar. So this one is asking us to evaluate all trig functions for the angle negative pi over 2. So what does negative pi over 2 look like? Well, that's 90 degrees, but going in the negative direction. So it's going to be here. And so again, this is one of the ones where we don't need to draw a triangle. We can just look at the picture and say, okay, the x coordinate is going to be 0, and then the y coordinate is going to be -1. Okay, so what is sine of this angle? Sine of negative pi over 2. Well, sine is the y coordinate, and so that's -1. So we'll see this one actually is kind of like flipped from the previous one. So cosecant of negative pi over 2, well, that's supposed to be the reciprocal of sine, so it's going to be 1 over sine of negative pi over 2. And so that is 1 over -1, and so it is also -1. Okay, what happens now with cosine? Well, cosine is the x-coordinate. And so in this case, the x-coordinate is 0, right, of our terminal point. And so the reciprocal of cosine is secant. So we're going to have 1 over cosine of negative pi over 2. And so that's going to be 1 over 0, and so that is undefined. Okay, so now we have tangent and cotangent, and we'll see that something a little bit interesting happens here. So tangent of negative pi over 2, well, that is going to be the y coordinate divided by the x coordinate, or you can think of it as the slope. And so notice that in this case, the terminal side is vertical. And so that would mean its slope is undefined. And we can also see that happening when we take the -1 over 0. So tangent is undefined. So with cotangent, it might be tempting to just say, well, tangent is undefined, so shouldn't cotangent also be undefined? But really, when you're evaluating cotangent at an angle where tangent is undefined, you don't want to kind of already have in mind that tangent is undefined. You basically just want to take the reciprocal kind of at this stage. So we want to rewrite it as 0 over -1. And so that way we can see that cotangent is actually equal to 0. And so really, I mean, maybe going back to where we originally defined these, the probably better way to think about cotangent is instead of thinking of it as 1 over tangent, remember that tangent was sine over cosine. So I think it's better to think of cotangent as actually being cosine over sine. And that way, even if tangent is undefined, that won't really influence the way that you find cotangent. So, figure out what the x-coordinate is, that's cosine, figure out what the y-coordinate is, that's sine, and divide those to find cotangent. So in this case, we get 0. So next I want to do a few more examples, and we'll see that these examples are going to be a little bit different than examples we've seen so far in terms of how we actually go about evaluating our trig functions. So first example says, let theta be the angle shown below. Evaluate all 6 trig functions for theta. So what is different about this question compared to some other ones we've done? Well, in this one, we are not told what theta is, right? It doesn't say, oh, theta is 7 pi over 6 or something like that. It just says theta is just this angle shown below. You might be able to estimate roughly what theta is, but that's not really the right way to approach this question. Theta is literally the angle shown below. You should not be trying to guess what angle it looks like. So what we are given is we're told what the terminal point is. So unlike other problems, a lot of the other problems, we've had to actually find the terminal point. This time it's actually handed to us. So one thing I just want to quickly mention that I think is a kind of a misconception that a lot of students will have. I've had students look at a problem like this and tell me, that point isn't on the unit circle. Like that's not one of the, that's not 1/2 and square root of 3 over 2. It's not one of the points on the unit circle. I just want to remind you that the unit circle is the set of all points that are a distance of 1 from the origin, right? It's a set of all points that lie along this circle. So I think it's really easy to get to attach to the picture of the unit circle that we've been working with, where we have all of our multiples of pi over 6 and pi over 4, pi over 3, and we have all these different x and y coordinates that kind of keep repeating the same numbers. But those are not the only points on the unit circle. Any point that lies on this circle is a point on the unit circle. And we can even verify that this point actually lies on the unit circle. We can verify that by plugging it into the unit circle equation, right? So 4 over 5 squared plus negative 3 over 5 squared. We would want to be testing whether that equals 1. And we would get 16 over 25 plus 9 over 25. And we're testing whether that equals 1. And it does, right? So 16 plus 9 would give us 25 over 25, which is in fact equal to 1. And so right there, we can see that this point does lie on the unit circle. And so it does lie in the unit circle. What I would say is that it's not, we can tell from this terminal point that this angle is not one of our usual familiar angles, right? It's not a multiple of pi over 6 or pi over 4 or pi over 3. It's some other angle. But again, we don't need to figure out what angle it is to answer this. How do we evaluate trig functions? We just need to know the terminal point, and we do in this case. So I'm going to color code this to kind of correspond to what we've been doing in other problems. Oops, that'll be blue. And so how do we evaluate sine, cosine, etc.? We just need to know the x and y coordinates of the terminal point. And so for example here, we can start by saying, sine of theta, well, that's going to be the y coordinate of the terminal point, and that is negative 3/5. And we can now do cosecant of theta, right? Because that's supposed to be the reciprocal of sine. So what's the reciprocal in this case? Well, the reciprocal of negative 3 over 5 is negative 5 over 3. So I'm not gonna write out 1 over sine of theta, because I think at this point we've done that enough times. And then cosine of theta, well, that's just the x coordinate of the terminal point. And so that's just going to be 4 over 5. And then secant, remember that one is the reciprocal of cosine, so that's going to be the reciprocal of 4 over 5, which is 5 over 4. And then finally, this one we have to do a little work for. So how do we find tangent? Well, tangent is going to be sine over cosine, right? Or the y coordinate over the x coordinate. And so sine over cosine would be negative 3 over 5 over, and then cosine is 4 over 5. And so as we've seen happen in some other instances, these denominators are going to cancel out with each other, and we're going to be left with just negative 3 over 4. And then cotangent, I guess I didn't leave myself quite enough space here, but cotangent of theta is going to be basically the reciprocal of this. As I mentioned, because there are some weird things with tangent being undefined and finding cotangent, it's usually better to calculate cotangent as cosine over sine. In this case, because tangent we know is defined, we can actually just take the reciprocal. Or you could set it up as 4 over 5 over negative 3 over 5, you would get the same result. But because tangent is defined, we can just take its reciprocal and say, okay, it's negative 4 over 3. So yeah, so why am I showing you this problem? Basically just to emphasize that everything we've learned about the unit circle and how to calculate sine and cosine and all the other trig functions, that is true for any angle. It's not just true for the angles that we've been drawing triangles for. So as long as you know what the terminal point is, you can find the trig functions regardless of whether you actually even know what the angle is. Okay, so this problem is a little bit different, but it's kind of getting at the same idea. So this problem is asking us, without using a calculator, and we'll get into actually using a calculator, that's kind of our next quick little topic. So we want to determine which of the following could be the value of sine over 3. So as I just said, we're going to talk about using a calculator. We'll see that you can evaluate sine of 3 using a calculator, but I want to kind of try to make sense of what sine of 3 would actually look like, in terms of the unit circle. So this looks a little bit different from things we've been doing, right? Because 3 doesn't have a pi in it. It's not like 3 pi over 4. It's just 3. But we should still assume that we're working with radians. Unless you see a degrees symbol, assume that you're working with radians. And so 3, means 3 radians. And so I want to think about, what would that angle look like? We're not going to be able to get it perfect, but we're going to at least be able to estimate what that angle could look like. And then that will help us to narrow down our list and figure out which one it could be. So what does 3 radians look like? Like what, of all the angles we know pi over 6, pi over 4, pi over 3, pi over 2, pi, which of those is 3 radians the closest to? Well, it's closest to pi, right? It's just a little bit less than pi radians. And how do I know that? Well, because pi is about 3.14, right? And so 3 radians is going to fall somewhere just a little bit shy of 3.14. And that means our angle is going to look, something like this. I'm probably exaggerating. It's probably even closer to being horizontal, but I just want to make sure you can actually see it. So does that make sense? So even though it's not a multiple of pi, we can just kind of figure out like roughly where that point is going to lie on the unit circle based on the fact that 3 is pretty close to pi. Okay, so now we can look at our list and try to figure out like which of these seems reasonable. So looking at our terminal point, we don't know exactly what the coordinates of the terminal point are. We shouldn't try to figure out exactly what they are, but we can figure out roughly what's going on here. So one thing we can tell is that the terminal point has a negative x coordinate and a positive y coordinate, right? Because it lies in the second quadrant. And so that can immediately get rid of, so remember sine is the y coordinate, so that immediately eliminates anything that has a negative sine value, because if sine is the y coordinate and the y coordinate is positive, then we can't have these two. So we're crossing these two out because we know the y coordinate is actually positive, not negative. Okay, so now we're left with 0.99 and 0.14. So which of those seems like it could be the value of the y coordinate of this? Well, remember that, if we're looking at y coordinates, forgetting about the circle for a second, the y coordinate, if you were like down here, would be 0, right? That's a y coordinate of 0. If you were up here, it would be 1. Because it's the unit circle, it has a radius of 1. And so does it look like our y coordinate is closer to 0 or closer to 1? Well, it's definitely closer to 0, right? Because our angle is so close to being horizontal, that means that the value of sine should be pretty close to 0. And so that means we can also eliminate this angle here. So 0.99, that is too big, right? So I'm going to cross this out and say this is too big. We can tell that the y coordinate is closer to 0 than it is to 1. And so that leaves us with the only option being this angle here. And so if you actually go into your calculator and type in sine of 3, you'll see that you get about, it will have a bunch of decimal places, but if you were to round it to 2 decimal places, it would be about 0.14. So again, my point here is that for any angle, regardless of whether it's one of the nice friendly angles that we've been working with, it is always true that the x and the y coordinate are what you use to evaluate sine and cosine. Okay, so I want to get a little bit more into this idea of actually using a calculator. So far, because I don't want you to get like the wrong idea about trig functions, because so far all of the examples we've done, maybe except for like the last two, we've been working with angles that are these nice multiples of pi over 6, pi over 4, pi over 3, etc. So when you're working with an angle theta that is a multiple of pi over 6, pi over 4, pi over 3, or pi over 2, and really, pi over 3 is actually already a multiple of pi over 6, and pi over 2 is a multiple of pi over 4. So, but I'm just listing them all out just to be very clear of the types of angles we're talking about. So when you have an angle that is a multiple of one of those, we can evaluate trig functions of theta by hand, basically using the unit circle. And when I say using the unit circle, I mean by drawing our special right triangles and figuring out what the sides are and using that to determine sine and cosine, and then all the other ones. However, those aren't the only angles, right? Like there are plenty of other angles. You know, any number could be interpreted as an angle in radians. We already saw like 3, right? 3 radians, that's an angle. 25 radians, that's also an angle. 327, that's an angle. Like any number can be interpreted as an angle in radians. So if you have an angle that is not, and actually let me kind of put kind of a shortcut word I'm going to be using here. So I'm going to be calling angles that are multiples of, actually let me highlight this whole part. So if you have an angle that's a multiple of one of these ones, I'm going to be calling those nice, in quotes, angles. Not to say that other angles aren't nice, but I think, you know, hopefully you'll know what I mean when I say nice or not nice angles. So if theta is not a nice angle, so if it's not one of those multiples, then we can't really use the unit circle to evaluate sine and cosine, etc., unless we're given additional information. So like the last 2 examples we did, we were given the terminal point on the first one, and then on the second one, it was multiple choice, right? So we could kind of like just use process of elimination. But if we're just given a random angle and it's not a nice angle, then you can't really use the unit circle to figure out exactly what sine and cosine, etc. are. You might be able to estimate, but you're not going to be able to get the exact angle. So what we need to do is use a calculator. And we'll do an example of this in a moment. And just to give some examples of angles that would not be considered like a nice angle, you know, pi is equal to 3 radians. Pi is equal to 5 pi over 7. That kind of looks like a nice angle, right? But it's not a multiple of pi over 6 or pi over 4 or any of those. It's a multiple of pi over 7. And so it's not going to correspond to any kind of special right triangle. You could have theta is equal to 529. Really any number that is not a multiple of one of these things I underlined in blue, it's still an angle. It's just not one of the angles we know how to draw a special right triangle for. So I'm going to do an example, like I said, in a moment, but I want to mention a few more things. So when evaluating using a calculator, to evaluate trig functions, make sure the calculator is in radians mode for now. You know, later on we'll do some examples working with degrees, but for now, angles are in radians. So you want to make sure that your calculator is in radians mode. And I can't tell you exactly how to do that on your calculator, but I'm sure if you Google your calculator name and how do I put it in radians mode, you can find the answer. Usually there's like a button, or maybe you have to go into the settings and kind of toggle between radians and degrees. This is probably like the most common mistake I see students make when doing calculator stuff, is just having the calculator in the wrong mode, and it will give you the wrong answer. So you want to make sure that your calculator is in radians mode. So I want to mention a couple more facts before we get into our example. So another one is that as we saw in these earlier examples, so even though we cannot use the unit circle to evaluate trig functions. Oops. Something funny is going on with my pen. Let's see. Trig functions, when theta is not a nice answer or a nice angle. It is still true that, for example, as we've talked about, sine of theta is the y-coordinate of the terminal point. And it is still true that cosine of theta is the x-coordinate of the terminal point, etc. I'm not going to write down all the rest of them, but all of these relationships are still true. So just to give an example of that, like in this example, we were not able to draw a special right triangle, but we did use the fact that the x and y coordinate are sine and cosine to kind of eliminate which answers could not be the value of sine of 3. And we'll do another example like this in a minute. But yeah, so even if you're not using the unit circle to evaluate sine or cosine of an angle, it is still true that if you could locate that angle perfectly on the unit circle, and if you could find the x and y coordinates of the terminal point, those still would correspond to sine and cosine. Okay, 2 more things to write down. I know this is going to be kind of like a wall of text, but I just want to make sure I get all of these out. So another thing to know is that to evaluate the reciprocal trig functions, you basically want to type 1 divided by whatever the original trig function is. And the reason for that is that for the most part, calculators don't have a button for the reciprocal trig functions. So for example, like let's say you wanted to, you were asked to evaluate cosecant of 5 pi over 7. So as we mentioned earlier, 5 pi over 7 is not a nice angle. Even though it has pi in it, it's not a multiple of one of the angles we know how to work with. So there is not really a way on most calculators to just type that in. What you would need to do instead is do 1 over sine of 5 pi over 7. So just be aware of that, and we'll do an example of this in a moment. But yeah, you basically want to figure out what sine is and then just do 1 divided by that result to find what cosecant is. Okay, very last thing to say before we get into another example. I do want to say that a calculator actually can be used even when you have a nice angle, right? So a calculator can be used to evaluate trig functions for nice angles. It can. You could use a calculator. However, I do expect that you know how to do them by hand. So I will require you to evaluate trig functions by hand on tests and quizzes when your angle theta is a nice angle. So you basically have to be able to tell, like, is this angle one of the ones that I know how to evaluate using the unit circle? If so, that's how I'm supposed to do it. If it's not, then that's where you go and use a calculator. So I will be looking out for that. And another thing to know is that for most calculators, if you use the calculator, it will give you a decimal approximation rather than an exact answer. And that's okay for these angles that are not nice angles. But for the angles that we're familiar with on the unit circle, your answer should always be exact. So if you're using a calculator, it might give you this rounded form, which really isn't what we're even looking for. Okay, so now that we've talked about all of that, let's look at an example here. So this problem says use a calculator to find sine of pi over 5 and cosine of pi over 5, and then we're going to use that information to label the terminal point of theta is equal to pi over 5. So first thing I want to say is that pi over 5, so what is that like approximately, just so we can kind of eyeball where it is on the unit circle. So how could we figure out what pi over 5 is? Well, remember, pi is 180. So if you do 180, and I guess actually I shouldn't even say equals approximately, it's exactly. So if you do 180 divided by 5, you'll find that that is 36 degrees. So that gives us kind of an idea of where to put it. So it's a little bit more than 30 degrees. So maybe something like this. So this would be pi over 5. That being said, even though we can figure out what it is in degrees and it's a nice clean number in degrees, it's still not a multiple of pi over 6 or pi over 4 or anything like that. So we're not going to be able to use our special right triangles. So this is not a quote nice angle, even though it kind of looks like it is. And so that means we want to type this stuff into our calculator. So if you type sine of pi over 5 into your calculator, making sure that you're in radians mode, you should find that it is approximately equal to, I should put approximate here, approximately equal to 0.59. And then if you evaluate cosine of pi over 5, you should find that it is approximately equal to 0.81. So, and actually, let me change the color of this. Okay, so now that we know this from our calculator, we can kind of work backwards to write down what the coordinates are of the terminal point. So now that we see that cosine is 0.81 approximately, that tells us that the x-coordinate of this point is approximately 0.81, and the y-coordinate is approximately 0.59. And we can kind of just check, does that seem reasonable? And I think it does, right? If we look at where this point lies, it looks like the y-coordinate is a little bit more than a half, right? It's a little bit closer to 1 than it is to 0. And then it looks like, it looks like the x-coordinate is pretty close to 1, right? The x-coordinate is further to the right than the y-coordinate is vertical. So it makes sense that cosine is bigger than sine. So basically we worked backwards here. Instead of finding the terminal point and then evaluating sine and cosine, we evaluated sine and cosine with a calculator and then used that information to label our terminal point. Okay, last question of the video is asking us to evaluate cosecant of pi over 5 and secant of pi over 5. So this is what I was talking about earlier. There's no button on most calculators to do this. So the way that we just do it is by using these reciprocal facts. So we would say, okay, cosecant of pi over 5, the way I can evaluate this using a calculator is I can do 1 over sine of pi over 5. And so if you type all of that into a calculator, you should find out that cosecant is approximately 1.70. And then similarly to find secant of pi over 5, you would type into your calculator 1 over cosine of pi over 5. And that would come out to be approximately 1.24. All right, so that is it for this video. In our next video, we'll do a little bit more with the trig functions. We're going to learn about something called the Pythagorean Identity, and that will be it. So I will see you in the next video.